Good morning, students. Today we will study about de Broglie equation. We know that light and other electromagnetic radiations have dual nature, that is wave nature as well as particle nature. But Louis de Broglie, who was a French physicist, he gave another idea about the matter, that matter particles, whether they are microscopic, means बहुत छोटे छोटे हैं, as well as macroscopic, बड़े वाले. All these particles of matter having dual nature, that is particle nature as well as wave nature. However, the wave associated with matter is known as matter wave, with the characteristic different from the electromagnetic wave. He correlated the two characters in the form of an equation, and that equation was known as de Broglie equation, and this equation was lambda is equals to h upon mv, where lambda is wavelength, h Planck's constant, this small m is the mass, and v is the velocity. Combinedly, mv, it is known as momentum, that is momentum is equals to mv. It is also represented by, it is equals to p. Momentum is equals to mv, which is equals to p. So p is equals to mv. So momentum can be defined as mass in motion, that is variable mass of different particles and motion, that is mass in motion. So next is derivation of de Broglie equation. De Broglie equation is derived from Planck's quantum theory and Einstein's equation, that is de Broglie relationship is derived initially for photon of light with the help of Planck's quantum theory and Einstein equation. We know that the according to Planck's theory, E is equals to h nu, so and nu is equals to c over lambda. This implies E is equals to h c over lambda. Give this equation as equation 1. According to Einstein equation, energy is equals to mass times of velocity of light square, mass mc square. That energy slowly changes to, or the mass slowly changes to energy when light falls on it. Give this equation 2, name equation 2. Okay, from 1 and 2 you can see the left hand side is equals to E. If left hand sides of equation 1 and 2 are equal, that is equals to E, then right hand sides are also equal. So from 1 and 2, h c over lambda is equals to mc square. So from here 1c will cancel 1c, so lambda will equals to h over mc, because you can also do in this way, that hc over lambda is equals to mc square. So lambda is equals to hc, it will go here, it will go here, so hc square, this will cut, so it will come equals to lambda is equals to h over mc. Now here this is c is velocity of light. If velocity of a moving material object is v, this equation will equals to lambda is equals to h upon mv, and mv we have studied that is equals to momentum, so lambda is equals to h upon p. So from here you can see that lambda is equals to h over p. Here h is constant, that is Planck's constant, and p is momentum. So you can say that lambda is inversely proportional to momentum. When you will move this inversely equation, that is when you will write it as lambda is equals to, then there will be proportionality constant, which is here equals to h, Planck's constant, divided by momentum. So lambda is wave length, that is wave nature is inversely proportional to particle nature, is inversely proportional to particle nature. So from here we can say that the wave and particle nature of the moving material object is inversely proportional to each other. That is, the wave and the particle nature of moving material is inversely proportional to each other. Particle and wave nature inversely proportional to each other. But there is limitation of this equation. Limitation of de Broglie equation. This equation holds good for the microscopic particles, but not for the macroscopic particles. So how it holds good for microscopic particles and not for macroscopic particles? Let us take one example, that an electron and a ball both are moving with the same velocity, that is 10 raised to power 5 meter per second. So de Broglie equation is lambda is equals to h upon mv for electron, and for ball it will be h upon mv. Just write values. The value of Planck's constant is 6.626 into 10 raised to power minus 34 kg meter square per second, divided by mass of electron is 9.1 into 10 raised to power minus 31 kg, and the velocity is given 10 raised to power 5 meter per second. Similarly here 6 for the ball, you will write here, this is v, 6.626 into 10 raised to power minus 34 kilogram meter square per second, divided by, here the mass of ball is 1 kg into velocity same 10 raised to power 5 meter per second. This value will come 7.27 into 10 raised to power minus 9 meter, and this value will come 6.6 something into 10 raised to power minus 38 meter. Now from these values you can say that the wavelength of electron wave is within the range of electromagnetic waves, and this can be measured. However, the wavelength associated with wall is very small. This is very small because this is 6.6 divided by 1 and 38 times 0. This is 7.27 divided by 1 and 9 times 0. So this is a large value. You are dividing 6.6 by large value and 7.27 by small value. So this wavelength is within the range of electromagnetic waves. So we can measure this. However, we cannot compare this with the electromagnetic waves. Therefore, it is not possible to measure the wavelength for the macroscopic objects. It was all about de Broglie equation.